The orbitals are written out in this little picture right here. And you can see, first of all, that on the far left side, we see s orbitals, which are basically spheres. The bottom one is 1s, and that's smaller than 2s. And 2s is smaller than 3s. So the n value, which is n equals 1, n equals 2, n equals 3, as the n gets bigger, the orbital gets bigger. So 2s is bigger than 1s, 3s is bigger than 2s, etc., etc. But before we do the other ones, we should talk about what the letters here are, because here we're seeing n and l together. So this is called NL notation, and we're going to see that both N and L are important when you want to figure out the energy of where the electrons are. Now, if you used, for example, in 1s, S means L equals 0. Stupid there on the left-hand side. Anyway, L equals 0 means S. So 1s, if you used N and L together, it would look like 1 and 0 or 10. And it's hard to know if you had 10 or 1 and 0. So that's why scientists use NL. They use a letter for L so that you know right away that N equals 1 and L equals 0. So if you have, for example, 3p, n equals 3, because 3 is the n value, and p means L equals 1. So for 3p, you would have n equals 3, L equals 1, etc., etc. And that's why they use it. Now, for 1s, 2s, and 3s, there's only one orbital, because L equals 0, m sub L equals 0, one value, one orbital. But when you get to L equals 1, which is p, then you have m sub L minus L to positive L, m sub L minus 1, 0, plus 1, 3 values. So that's when you start to see the orientation effects. So when you have L equals 1, the p orbitals, you're always going to have an x, a y, and a z. That's why they say 2px, 2py, 2pz, and then the bigger versions above, 3px, 3py, 3pz. Pretty cool. When you get to d's, L equals 2, then you start to have m sub L minus 2 to positive 2. That's minus 2, minus 1, 0, plus 1, plus 2. 5 allowed d values. So you start seeing 5 of them, and the orientations get a little bit more complicated, but you just have to realize there's 5 different versions, 5 different orbitals when you get to the L equals 2, i.e. d subshell. So it's pretty cool. So this is why they use NL notation. All right, both the number for N and really the number for L are important for energy, but you can't put the numbers together. It might be confusing. So that's why people use letters for L. Kind of cool. So here's an orbital. We have n equals 3, L equals 1, m sub L equals minus 1. The question is, what type of orbital is this? So we'll use the NL notation. So the number will start with 3 because that's what n equals 3 is. And L equals 1 means it's a p subshell. So we would call this a 3p subshell. All right. 4d would be n equals 4, L equals 2. 3s would be n equals 3, L equals 0. 3d would be n equals 3, L equals 2. So you can start to see what it is. You don't need to know which of the orbitals it is. You just need to know it's one of those types of orbitals in the 3D set. Like you don't know if it's 3D z squared or 3D xy, or in terms of 3p, you don't know if it's 3px or 3py, but you at least know it's 3p, and that's cool. Nodes are places where the wave doesn't exist. And we saw in standing waves, there were places where the wave went up and down, and right in the middle was a node. There were no density. Well, it's important to know that there are 2 types of nodes when it comes to orbitals that are really important. And why they're important is because electrons are kind of the glue that holds molecules together. And if there's no electrons there, there's no glue to hold anything together. So nodes are places where electrons aren't present and you can't make a bond there. So there's 2 types of nodes. One is called spherical or radial nodes, and to figure it out, you just go n minus L minus 1. So let's look in the upper right hand corner. That is a 1s orbital. So n equals 1. S means L equals 0. So in this case, there would be n minus L minus 1, 1 minus 0 minus 1, 0 radial nodes. But when you go to the lower one, when you go to 2s, now n equals 2, L still equals 0. 2 minus 0 minus 1, 1 radial node. And you can see in the middle there, there's kind of like a white sphere. That's the node. It's an area where you can't have any electron density, so you won't have any bonds form right there. And you can keep going 3s and stuff like that. Now, another kind of node is called a planar node, and a planar node is like a sheet of glass that separates the different parts of the nodes, and the planar nodes just equal L. So for an S node, there are no planar nodes, but when you get to P, which is L equals 1, then you're going to have one planar node. This is one of those figure eights I talked about, and this right there shows the node. There's an area between the left and the right parts of the figure eight where there's no electron density, so you're not going to make any bonds right there. Likewise, D means L equals 2, so you'll have two sheets of glass kind of separating those parts out. L equals 3, 3 planar nodes, etc. like that. So again, nodes are just important because there's no electron density to make bonds. That can be important when you get to certain types of concepts when making molecules. Let's just go through some examples of types of orbitals. We'll look at some s orbitals. On the left-hand side is a 1s orbital, and you can see it's pretty small. It has 0 radial or spherical nodes and 0 planar nodes, not too much happening. If you go to the bigger 2s, though, then you can see right away it is, first of all, a bigger a bigger orbital, I should say. It's bigger than the 1s. This has, though, one spherical node. And if you look at this picture on the right, if you look very carefully, there's kind of like a white circle that goes around. That's the spherical node. It's actually an area where you can't make any electron density. In the upper graph, you can see it right there. That's the spherical node. That's like a slice of the spherical node right there. Anyway, just realize there's one radial node. If you go to the bigger 3s, then you even have 2 spherical nodes, and you can see them both in that diagram. Now, that kind of mesmerizing picture in the upper right-hand corner is trying to show you then the spherical nodes. And you can see there's like circles within circles. The circles can represent the spherical nodes where there's no electron boundaries happening. P orbitals are somewhat similar. So on the left-hand side there's a 2p orbital. It's 2px technically. We don't have to worry about that. Now 2px has 0 spherical nodes, but because p means L equals 1, you will have a planar node. So you can see in the middle there's no electron density happening. That's where the nucleus is in this case, which is kind of cool. If you go to the bigger 3px, then you do, first of all, have a bigger orbital because 3 is bigger than 2. You still have the planar node, but now you actually have a spherical node. So there's more complicated types of areas with no electron density as the orbitals get bigger. But again, all of these more or less look like a figure 8. Some of them are funkier than others, definitely, but that's kind of the idea. So the question here is how many total nodes are in a 4p orbital? Now, 4p means n equals 4. That's what the 4 means. And SPDF, P, means L equals 1. So the number of planar nodes equals L. There's going to be one planar node. And spherical nodes, or radial nodes as they call them in this book, n minus L minus 1. So for this 4p, that would be 4 minus 1 minus 1, 2 radial or spherical nodes. So if you have one planar and 2 radial or spherical nodes, you're going to have a total of 3 nodes in the 4p orbital. So again, to figure questions like this out, you have to calculate both planar and radial or spherical. In this case, it's 1 planar, 2 radial, so for a total of 3 nodes. The Ds are pretty cool looking. Ds we're going to see are the domain of transition metals, which are one of my favorite. And you can figure out radial and spherical and all that kind of stuff. Now, most of the Ds look like 2 figure 8s together. And if you look at 4 of the 5 of them there, that's kind of what they are. It's like 2 figure 8s kind of squished together. And they're on different axes, all that kind of jazz. But check out the 3D Z squared orbital in the kind of middle lower part there. I call that the donut orbital. It's like like one figure 8 with a donut around it. And again, the math is just crazy how they figured that out, but it is cool. That's always the one kind of weird orbital in these. So again, just remember that when you have a d orbital, that means L equals 2. And m sub L goes from minus L to plus L, which would be minus 2 to positive 2, minus 2, minus 1, 0, plus 1, plus 2, 5 d orbitals. And this is what we're seeing here. So each of those has a different m sub L value. That's why there's 5 of them. They're kind of cool to look at. Which orbital would you expect to have the most volume? All right. Now, volume, of course, is three-dimensional space, and you've seen many different kinds of orbitals here. But the important part is that as n gets bigger, the orbital itself gets bigger. So more than the SPDF, I would just predict that the 4 in 4F would have the most volume. F has a lot of volume as well. We'll see some pictures of those here in a little bit. But the biggest thing is that n is proportional to the size, and as n gets bigger, the volume gets bigger. Probably the 4F would have the biggest volume. The F orbitals, there's 7 of them, and they get even more interesting. So on the right-hand side there, you see the 7 F orbitals, and more or less, they're kind of like 3 or so figure 8s put together, but you do start seeing some donuts. So in the top one there, the FZ3 thing there, you begin to see like 2 donuts inside. So you're seeing the progression here of the different orbitals. At the top on the left-hand side, this is an S orbital. The second row down, if you will, this is the P set. So you have PX, PY, PZ. The next set down is the D set, which are ones we saw in the previous slide. And then these 2 right here would represent the Fs. But notice the patterns. You've got 1 orbital in S, 3 orbitals in P, 5 in D, 7 in F, etc., etc. Quantum mechanics is filled with patterns. This is one of the patterns you can check out. Let's do an example where we want to figure out the different quantum numbers for the n equals 3 shell, okay? So we're starting with n equals 3, and we want to find L, the subshell letters, the NL notation, the m sub L values, and the number of orbitals. And this will be a good idea to show the different things we've talked about so far. So first of all, when n equals 3, L values go from 0 up to n minus 1. So 3 minus 1 means it's going to go up to 2. So L always starts at 0. It's going to go up to 2. There's going to be L values of 0, 1, and 2. L and n can never be the same thing, but they will be up to n minus 1. And notice that means 3 L values here for n equals 3. Now the letters that go along with this is where you do the SPDF notation. L equals 0 is S, L equals 1 is P, L equals 2 is D, etc., etc. So instead of talking about L equals 0, scientists will usually say the S subshell or something like that. So the NL notation will be the number 3, because this is the n equals 3 shell in front of those letters. So 3S would be the first one, 3P would be the second one, and 3D would be the third one. So you can see how this stuff begins to fall in place. You could have, for example, a 4S, 4P, and 4D. So this is a way to distinguish between the two of them. M sub L values depend on L. M sub L values go from minus L to positive L. 0 is always going to be a value. So for 0, that just means M sub L is going to be also equal to 0, because minus 0 to positive 0 is just 0. But when you get to L equals 1, then you have M sub L minus 1 to positive 1. So that would be minus 1, 0, plus 1. There'd be 3 M sub L values for that. And when you get to L equals 2, minus 2 to positive 2, you can see there's 5 different M sub L values that are possible. So because there's 1 M sub L value, that's why there's 1 orbital. Because there's 3 M sub L values when L equals 1, that's why there's 3 orbitals. 5 for the D, etc., etc., which is what we saw in that last slide. And then the number of orbitals literally equals the number of allowed m sub L values. And remember, L value, m sub L equals 0 is an allowed value, just like all the other ones. So for the first one, there would be one orbital because m sub L equals 0 is allowed. For the second one, we have -1, 0, +1. Those are 3 allowed values, 3 orbitals. 5 for the last one, etc., etc. Now, if you're starting with n and you want to know the total number of orbitals, you can just go n squared. So 3 squared will get you 5 plus 3 plus 1, or 9, all right? And that's kind of a quick and dirty way to do these kind of things. Quantum mechanics is filled with little expressions like that. Some people like them, some people don't. It's just one I wanted to tune you into. Some people prefer the train track model when thinking about quantum numbers, which is fantastic. We just looked at the n equals 3 example right there. And n equals 3 broke down into L values of 0, 1, and 2. So when L equals 0, there was only one m sub L value, one orbital. But when L equals 1, there were 3 m sub L values, or 3 orbitals. And when L equals 2, there were 5 m sub L values, or 5 orbitals. And you can do the same thing for 2 and 1 and stuff like that. So whichever method you use, it's important stuff to figure out. And again, it's not too hard. And again, what's kind of cool is this is all the results of some pretty high-level math, and they were able to do it. Pretty awesome. Wolfgang Pauli came along and realized that if you're going to have an atom, you have to have each electron have its own set of quantum numbers. So no two electrons in the same atom can have the same set of quantum numbers. And it has to do with energy and lots of different things, which is cool. So because the spin quantum number can be plus or minus 1/2, that means that each orbital, each of those values of m sub L, can hold 2 electrons. One will be spin up and one will be spin down. But you can't have more than 2 electrons, and there's a lot of implications for that. So Pauli was pretty cool to think about that, and that's going to have a lot of implications. So when n equals 1, L is going to equal 0, and m sub L minus L to plus L is going to be equal to 0 as well. So that's going to have a single orbital because we have only one value of m sub L, and that orbital is going to be 1s. That's the NL notation. So n equals 1, L equals 0 is s, 1s. And what that also means then is that because each electron has to have its own set of quantum numbers, there's going to be 2 electrons that can hang out in that orbital. So the first electron will be n equals 1, L equals 0, m sub L equals 0, m sub s equals plus 1/2. The second electron, n equals 1, L equals 0, m sub L equals 0, m sub s equals minus 1/2. So there are going to be 2 electrons per orbital, and that's really important. And this is all based on what's called the Pauli exclusion principle. And it just says that 2 electrons have to have different quantum numbers. The idea for this is that, let's say we wanted to invite electron number 2 to our party, but we don't want to invite electron number 1. Well, in theory, all these energy quantum numbers just refer to a type of energy. So we could invite the one electron, but not invite the other one. That's kind of the idea. Like if you wanted to send a letter, you'd want to send it to someone specific, maybe at a house, but not the whole house in general. That's kind of a weird way to think about it, but it does actually work in this context. Now, when n equals 2, then you're going to have a 2s orbital, and you're going to have the 3 2p orbitals. So if you look back on the train track, the n equals 2 split off to 2s, and there were also 3 2p tracks. So each of those is an orbital. There's 4 orbitals total when it comes to n equals 2. So on the right-hand side there, I have the different values of what's going on. The first column is just the number of the electrons. There's 8 total. All of them are n equals 2. L can be 0 or 1. When L equals 0, m sub L is just going to be 0, so you can have positive, negative 1/2 like before. Those are the 2s orbitals. But when L equals 1, then you have M sub L minus 1, 0, and plus 1. And you can see that each of those has two M sub S values. So final part here, the 2p orbital can hold up to 6 electrons. The S orbitals can only handle 2. But if you sum up all of these, there are 6 electrons in the 2p. We're going to see that all the p orbitals hold 6 electrons, all of the s orbitals hold 2 electrons. So pretty cool. And maybe you recognize some of these things, what we'll be talking about here in a minute, but either way, we'll get a little bit further. Now, these next couple slides are just informational. Don't get real stuck on them. But because of these different set of quantum numbers, you start to have more and more electrons possible. So this is for n equals 3. When n equals 3, you can have 3s, you can have 3p, and you can have 3d. And notice that the s's will hold 2 electrons. The p's, when you count them up, 8 minus 2 will hold 6 electrons, and there's a total of 10 electrons in the d orbitals. So you can see here some patterns going from 2 to 6 electrons when you go from s to p to d, you go to 10. There's a difference of 4 between those, which is another way to think about them. And just for completeness, let's do n equals 4, but it gets a lot more complicated. I can't even put it on the same page anymore. So when n equals 4, you have s, you have p, you have d, and these over here on the right represent the f's. So you're going from 2 to 6 to 10 to 14. But again, note, all of those quantum numbers are different. And they're different from n equals 3 and n equals 2 and n equals 1. This is the idea of Pauli exclusion principle. Now, what we're going to use here in a little bit is that S's always hold 2, P's always hold 6, D's always hold 10, and F's always hold 14. So we'll think about that here in a little bit.
In a single electron atom, hydrogen, subshell energies depend only on the subshell's principal quantum numbers. In a mini-electron atom, the presence of electrons in one subshell affects the energy of other subshells. Consequently, the subshells are not filled simply on the basis of the principal quantum number.
Bohr's expression for the energy of electrons only involved n. It was minus RHC over n squared, if you remember, and RH and C are all constants. So Bohr thought it was just n, but in reality, when you do a better quantum mechanic analysis, it's actually more, the energy is more about n plus L. So when you figure out n plus L, you get the little order described on the right-hand side there in the video. And you can see how 1s is lowest energy. That's going to be the first one to get filled in, and then 2s and then 2p after that. So 2p is a little higher energy, 3s is higher, 3p, 4s sneaks in before 3d, etc., etc. So this is quite a change because in Bohr's model it was just n, but in the real world it's n plus L. Now M sub L values don't affect the energy. They're considered degenerate, and degenerate in science means they're all the same energy. All right, I have different interpretations of degenerate when I hear that term, but in science, just the same energy. And again, remember that M sub S positive 1/2 is a little lower energy than minus 1/2. So you always want to start with an up arrow and then put a down arrow. So if you're filling electrons in, the first electrons always will be 1s, then you'll put 2s, then 2p, etc., etc. And the little cats right there are trying to demonstrate some quantum stuff, which is kind of cool. An Aufbau diagram is something you can write on the back of a piece of paper that will help you to understand how electrons get put in. And so what you do to write the diagram is on the left side, you start with 1s, then go 2s, 3s, 4s, all the way up. And then you go up and over 1 to start 2p, then go 3p, 4p, etc. Up and over 1, start 3d, 4d, etc. And then up and over 1, 4f. And if, by the way, you had a 5G, it would be right here, etc., etc. But in an Aufbau diagram, you draw these diagonal arrows. So the first arrow is just through 1s, the second arrow is through 2s, then you go 2p and 3s, etc., etc. And these arrows are what you follow when you're assigning electrons, which is really, really cool. You can also read the periodic table. Now, this is a little bit more advanced, but you can do this as well because electrons are filled in according to the Aufbau diagram. And what you can see here is that hydrogen and helium are both 1s, and lithium and beryllium are 2s. Then these are 2p, 3s, 3p, etc. Then it gets 4s, 3d, and stuff like that. We'll talk about this more a little bit. The hard part when doing electron configurations is that 3D gets filled in before 4P. There's some weird things like that. So this is where the Aufbau diagram can be really helpful when we start talking about it. The S block elements are the 2 columns on the left-hand side plus helium. The P block elements are kind of the salmon-colored thing. They're the 6 columns on the right-hand side. The D blocks are the yellows in the middle, and the F blocks aren't showing, but they'd be the lanthanides and actinides. So when you're writing electron configurations, the most common way is to use what's called spectroscopic or SPDF notation. And on the right-hand side there, this is an example of the electron configuration for hydrogen. So you use the NL notation. So hydrogen has N equals 1 and L equals 0, which is S, 1s. And then the superscript shows the number of electrons. So hydrogen has 1 electron, and earlier we saw the first electron, N equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. We always write the positive one first. That's 1 electron. That's the superscript right there. So that would be the SPDF notation for hydrogen, and that's what we'll use most of the time. There is, however, what's called orbital box notation, which can be helpful for magnetism. We'll talk about that later. So this is the spectroscopic notation for helium. Now, helium, if you remember from our conversation last chapter, helium is number 2 on the periodic table, which means 2 protons, and a neutral atom of helium would have 2 electrons. So the first electron would be N equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. And the second electron, N equals 1, L sub 0, M sub L equals 0, M sub S equals minus 1/2. So we would write that as a spin up, which is the green arrow, and then a red arrow spin down. And you can put the spin up first and the spin down later. That doesn't matter. So orbital box shows that you have 1 electron that's up and 1 electron that's down. And the number of arrows equals the number of electrons, which is the superscript right there. So spectroscopic and orbital box will be important as we go through, and we'll look at some examples as to how this works out. So when chemists talk about electrons in atoms, this is what they'll use. They'll use orbital box and or spectroscopic notation to figure out how this works. Lithium is number 3 on the periodic table. It has 3 protons. The atomic number is 3, but the neutral atom of lithium would have 3 electrons. So knowing that 1s is always filled in first, there would be an up and a down, and a third electron would be spin up in the 2s because 2s is the next one to get filled in. Remember, these electrons always start at the bottom and kind of move their way up. Now, because this electron is by itself, a spin up without a spin down, lithium is paramagnetic, and that's the advantage of the orbital box. It does a great job showing it. But you could also write 1s2, 2s1, and that would be great. And make sure you put the 1 there, the superscript. Don't write just 1s2, 2s. That would be ambiguous as to the number of electrons. It's always 1s2, 2s1. Beryllium, right to the other side of lithium. Beryllium has 4 electrons total. That has the same electron configuration as lithium, but with 1 more electron. Now, to put an electron in the 2p box would be higher energy, so it's better to have a spin down in the 2s orbital. So beryllium would be 1s2, 2s2, 4 electrons total. And because every up electron has a down electron, beryllium is diamagnetic, not attracted to magnetic fields. So don't be thinking beryllium's going to do things around magnets. Boron is number 5, 1s2, 2s2 like the other two. This has one 2p electron. Again, 2p would be the next one to get filled in. Spin up arrow before down arrows. One unpaired electron would be paramagnetic. So again, 1s2, 2s2, 2p1 is one way to say it, or you could write orbital box, 1s filled 2, 2s filled 2, 2p1. Both are great. Now, when you get to carbon, something special happens, and I want to talk about it. So carbon has one more electron than beryllium. Thanks for playing. It has one more electron than boron, so it has 6 total electrons. It's going to be 1s2, 2s2, 2p2, but you have a choice where the 6th electron goes, because you could put it in the same box as the 2p1, so you'd have an up and a down together. But what scientists have found, what is specifically Hund found, is that you have a lower energy configuration when electrons are placed in their own orbitals first. So you never see a 1s2, 2s2, 2p2 where both electrons are in the same box, in the same orbital. You always see them in separate boxes first. So Hund's rule just says that you always want to place electrons in their own orbitals first as long as possible. After a while, you have to start pairing up, but at first you want to keep them far apart. And remember, these electrons are all negative, and negative charges repel each other, so it makes sense to try and keep them as far apart from each other as you can. Hund's rule is exactly what that means. Just put them each other. So this is paramagnetic. It would be diamagnetic if you paired it up. We would also say that carbon with 2 unpaired electrons is more paramagnetic than boron with 1 unpaired electron. The more unpaired electrons you have, the more paramagnetic, the more interested in magnetic fields it is. Nitrogen would have 1 more electron than carbon. We're going to use Hund's rule, put each electron in its own box. We're not going to pair anything up. This is the most paramagnetic element we've seen so far. 3 unpaired electrons, 1s2, 2s2, 2p3. Oxygen, 1 more electron than nitrogen. Now, oxygen has an electron that has to go somewhere. It's higher energy to go to 3s, so now we're going to start pairing it. So with oxygen, we start pairing electrons up. So oxygen would only have 2 unpaired electrons, as it turns out, 1s2, 2s2, 2p4. Fluorine, with 1 more electron than oxygen, will pair up another one of those paramagnetic atoms, 1s2, 2s2, 2p5, but it's also paramagnetic. Again, nitrogen would be considered most paramagnetic because it has the most unpaired electrons. 3 unpaired is more than 2, which is more than 1, etc., etc. When you get to neon, you have 10 total electrons. That's 1s2, 2s2, 2p6. And at this point, all of the electrons are paired up. Everything has a pair. So neon is definitely diamagnetic. All right, no interest in magnetic fields. So this is now the end of the second period, which periods go left to right on the periodic table. So at this point, everything is paired up. So notice that for all of the elements we've seen so far, helium, number 2, beryllium, number 4, and neon, number 10, those are the only ones that were diamagnetic. Most of the elements on the periodic table are considered to be paramagnetic because they have 1 or more unpaired electrons. But also notice at the end of the p orbitals there, everything is diamagnetic. Same thing at the end of the s orbitals there, everything is diamagnetic. When you get past neon, a lot of times chemists will use what's called noble gas notation or core notation. And so, for example, for aluminum, which is 3 more electrons than neon, you would have 1s2, 2s2, 2p6, 3s2, 3p1. And that's a lot of syllables, obviously. So what chemists will use is they'll go backwards to the nearest noble gas and put it in square brackets. So the most recent noble gas was neon, so you'd write neon, Ne, in square brackets, and then whatever is left. So neon 3s2, 3p1, which is kind of cool. This is what they call core notation, and it's pretty awesome. So all of the group 3a elements are going to have this kind of notation. They'll have some kind of core, a noble gas core, and they'll have, depending on their period number, they'll have ns2, np1 electrons. Some of them will have Ds. We'll talk about that in a second, but it's kind of cool. And the reason why these all have the same pattern is why they all kind of react the same. And this is something we'll build on in later lectures too. Phosphorus has a total of 15 electrons. It's group 5a, 1s2, 2s2, 2p6, 3s2, 3p3, which is a lot of words. Or you could just say neon 3s2, 3p3, and that's why scientists like it. So this is another example. Everything in group 5a has an ns2 np3 outer core. Some of them have the Ds. We'll talk about that later. But anyway, it is kind of neat. And this is why everything in the same group kind of reacts the same. So in the last chapter, I said you should really know groups 1a and 2a, alkali and alkaline earth metals, as well as groups 7a and 8a, which were halogens and noble gases. Those groups have very similar reactivity, and that can be kind of helpful when you're a chemist. Chlorine is one of the halogens. It's in group 7a. And the question is, what is the electron configuration for it? So 17 electrons is what we're going to try and put here. So let's say that you are totally confused by what this is all working out, but you know that chlorine is number 17. Well, one way to answer questions like this, and it's not foolproof, but one way is to literally count the number of subscript numbers. So as an example of that, let's look at answer C. C has 1s2, 2s2, 2p5. And if you count those superscripts, that's 2 plus 2 plus 5. That's a total of 9 electrons. And we want a system with chlorine that has 17 electrons, so that's not enough electrons. So answer C is not correct. That's actually the electron configuration for fluorine, if you remember earlier. So if you look at these different superscript numbers, all of them are not quite 17 except for B. And B, if you count that up, 2 plus 2 plus 6, that's 10. Plus 2 plus 5, 7 more, 10 plus 7, 17 total electrons. So that does work sometimes. Now, it's not perfect, all right, but that is one way that you can do these kind of configurations. So A right there would have a total of 12 electrons. That's magnesium. D has a total of 18 electrons. That's argon. E, I believe, has a total of 20, which is calcium. So you get the idea here how this works, but it's a cool little tool that can help you out sometimes. Now, main group elements are elements in groups 1a and 2a on the far left, and groups 5a through 8a on the far right. Now, this periodic table is using 13 through 18. That's what they call the international version of the periodic table, which can be helpful. However, for our purposes, think of boron in group 13 there as being 3a, and helium and neon are officially groups 8a on the periodic table. But anyway, main group metals are different than transition metals, which are in the middle, as well as lanthanides and actinides, which are the two rows there on the bottom. And transition metals are basically the ones that have d orbitals, and lanthanides and actinides are going to use pink orbitals. Lanthanides and actinides are going to use f orbitals. So this is a nice way to kind of think about it. The s's are the two columns on the left-hand side in helium. The p's are the 6 columns on the right, not including helium. The transition metals are the groups in the middle, and those are essentially d electrons, while the lanthanides and actinides at the bottoms are f orbitals. When it comes to transition metals, almost all of them have some kind of noble gas core, NSX, N-1 dy, all right? And I'm sure that's as clear as mud, so we'll show some examples of that here in a little bit. Likewise, lanthanides and actinides have some kind of core, NSX electrons, N-1 dy, so some d electrons, and N-2 Fz orbitals, all right, but with exceptions. So again, transition metals, kind of the middle group there, chromium, iron, those kind of things, copper, very, very common. Lanthanides and actinides can be things like uranium and cerium, plutonium. So these are things that we definitely know about and hear about, and it would be cool to talk about their electron configurations. So these are just some examples of how this works. So potassium and calcium, I think, are probably going to start looking more familiar to you. They both have an argon core and a 4s1 or 4s2 configuration, no problem. Scantium is number 21 on the periodic table. So it has the same electron configuration of calcium, but with a 3d1. So earlier with transition metals, it said N-1d electrons. That's because you're in the fourth period. 4 minus 1 is 3. So that starts the 3d electrons. Titanium, one more electron than scantium, would be 3d2. Vanadium would be 3d3. But look what happens when you get to chromium, because chromium would have one more electron than vanadium. And for whatever reason, electrons jump ship from the S to the D. So instead of chromium being a 4s2 3d4, the actual configuration is 4s1 3d5. And this is one of the exceptions to the so-called N plus L rule. Now, when you get to manganese, it goes right back to the old orbital, to the old pattern, 4s2 3d5, etc., etc. Copper is also an exception. Instead of 4s2 3d9, it's 4s1 3d10. So there are some exceptions to these electron filling rules on the periodic table. The N plus L rule is breaking down. So this is an important part to talk about, because in science, not everything is known. Those silly cloud speeches that Lord Kelvin gave in 1900 are so wrong. So N plus L rule works really well most of the time, but not all of the time. So maybe one day this is something that one of you will work on, and I'll have a better description as to how to describe electrons going in. So just realize N plus L does not work perfectly. There are these anomalies. And again, one day maybe one of you can figure out a better theory, and I can talk about it instead of these weird exceptions to the N plus L rule. If you want to form anions, negative ions, or positive cations, positive ions, you can do that with these two. And I'm going to show some examples here with orbital box. So anions, negative ions, you would literally just add the additional electrons using normal rules. So on the left-hand side here, we have phosphorus. And on the right-hand side here, we have the phosphorus minus 3 ion, phosphide ion. Phosphide has 3 more electrons than phosphorus. And so you can see what happens here. They just filled in those 3 paramagnetic boxes and made them all diamagnetic. So phosphide has a neon core, 3s2 3p6, or an argon core. So to make an anion, you just fill in the lowest unoccupied spots to figure out what the electron configuration is. No problem. Cations, positive ions, are a little bit different, but a similar idea. When you want to make a positive ion, you remove one or more electrons from the subshells of highest N or highest N plus L. And I'll talk about what that means here in a little bit. Now, aluminum likes to make aluminum plus 3. So that's removing 3 electrons. So highest N or highest N plus L, we're going to take them from N equals 3 because that's higher than the 1s2, 2s2, 2p6, the N equals 1 and N equals 2 of the lower ones. So we're going to take away the 3s2, 3p1 electrons to make 3p0, if you will, and 3s0. We're going to be left with 1s2, 2s2, 2p6. So aluminum 3 plus has a neon core. Now, what we would do here is we would take away the 3p1 first, technically, and then we take away the 3s2 electrons after that. But it doesn't make a difference because we're taking away 3 electrons. The end result, aluminum 3 plus, will have a neon core. So here's an example of a question you might see. The electron configuration 1s2, 2s2, 2p6 represents which ions and or atoms? And we've got here the sodium ion, the oxide ion, the magnesium 2 plus ion, the neon atom, or all the above. So one thing you could start with here is adding up the superscripts like we talked about. So 2 plus 2 plus 6, those superscripts represents 10. So that means neon is going to have a 1s22s22p6, definitely. However, sodium has a total of 11 electrons. And if you take away one of the electrons to make it positive 1, 11 minus 1 is going to give it 10 electrons. And 10 electrons is 1s22s22p6. Sodium plus 1 is also going to be this configuration. Same thing with magnesium. Magnesium normally has 12 electrons, magnesium 2 plus would be 2 less than that. That's going to take away from the 3s electron shell and subshell. So that means magnesium 2 plus with 10 electrons also would have 1s22s22p6. And oxide, O minus 2, is going to be oxygen, 1s22s22p4 with 2 extra electrons. And if you add electrons, you'll add the 2 extra electrons to the 2 spaces that were paramagnetic before. We showed that earlier. Oxide also has a 1s22s22p6 electron configuration. So all of these are 1s22s22p6. And sometimes in lecture, I'll talk about how noble gases are like the cool kids in the back of the bus. And everybody in the bus wants to be like the cool kids in the back. The atoms themselves will often obtain a noble gas notation to be like the cool kids. So sodium loses an electron to become sodium plus, because it's going to have the neon core. Oxygen wants to gain 2 electrons to be like neon, have its same electron configuration, etc., etc. It's a juvenile thing, but there is stability in having electrons equal to one of the noble gas configurations. If you have a transition metal, there's a little bit of a twist here I want to talk about. When you make a cation, you remove the electrons first from Ns and then any N-1 electrons. So highest N first, then highest N plus L. So with transition metals, 4s gets filled in before 3d. If you look back at the Aufbau diagram, 4s gets filled in before 3d, 4p after that, etc., etc. So if you're making iron 2 plus, you need to remove the electrons from the highest N, 4, before you do the N equals 3. So iron plus 2 still has 3d6. Those electrons haven't changed. And why that's kind of weird is that the 3d6 were the last electrons in, if you fill them in that way, but they're not necessarily the last electrons out, because 4 is higher than 3. 4s electrons come out before 3d. Now, if you make iron plus 3, then you start whittling away at the 3d electrons. So iron plus 3 would have a 3d5 configuration, etc., etc. So you always want to remove electrons from the highest N first when making cations. And spoiler alert, this is big time important for transition metals, lanthanides and actinides, because you almost always remove those Ns2 electrons first before you remove any Ds or Fs. Magnetism, super important, also important when it comes to transition metals. And again, you can totally figure this out. So some of them will be paramagnetic, some of them will be diamagnetic. Zinc 2 plus, when you figure out zinc, zinc has 4s2, but you take away those 4s electrons first. Zinc 2 plus, every up has a down in the d orbitals, it's going to be diamagnetic. But most of the transition metals will be paramagnetic when they're ionic. You can see that some of them have more unpaired electrons than others. Again, more unpaired electrons means more paramagnetic, and less unpaired electrons means less paramagnetic. So manganese 2 plus would be more paramagnetic with 5 unpaired electrons than iron plus 2 with only 4 unpaired electrons. So here's a question you might see. It says, which ion corresponds to the following electron configuration? Now, notice here that this has an argon core, an empty 4s box, and 3d electrons. And if you count the up and the down arrows, there are 7 electrons there. So 3d7, okay? So knowing that it has, first of all, an argon core, it cannot be answer B, because rhodium is not in in the argon set. It would be the next one down. It would have a krypton core. So B is out. All right. So if it has a 3d7 and no 4s, at the very least, it had to lose 2 electrons. So be positive 2. So if you look on the periodic table and you start with scantium, that would be 3d1. Right next door would be titanium, 3d2. And if you go over to 3d7, you should find cobalt. So cobalt plus 2 has an argon 3d7 configuration. So on the right-hand side there, I have the neutral atom electron configuration on the left and what it would be on the right-hand side. Remember, all the S's go out first. So iron plus 3, the 4s2 electrons are out first, and you'd lose one more electron to make 3d5. And then the same thing like for nickel there on the bottom, you'd have argon 4s2 3d8. First 2 electrons out are 4s, so nickel 2 plus would be argon 3d8. But cobalt plus 2 would be argon 3d7, and that's what we're looking for, which is kind of cool. On the periodic table, which is very useful to chemists, there are some patterns, some periodic properties, there's some columns called, that will allow you to quickly tell which atom is bigger or smaller, or more into electrons, or more metallic, lots of different things. Now, these are just trends. They're a little cheesy, but they do sometimes help when asked random questions at different times. And the 4 we're going to look at in this particular section, more than anything, are the sizes of atoms, both the atoms and the ions, the ionization energy, how much energy it takes to remove an electron, the electron affinity, which is actually an energy change when electrons are added, and we'll also briefly talk about what's called electronegativity, which is how interested elements are in attracting electrons. Now, electronegativity is going to be more for the next chapter, so I won't talk as much about that here, but we'll talk about the first 4 and how the periodic table can be used to figure these things out. Now, punchline here is that sizes of atoms and ions will get bigger as you go left and down the periodic table, and all the other ones will get bigger, more or less, as you go up and to the right on the periodic table, and we'll talk about this here in a little bit. Sizes generally get bigger as you go left and down the periodic table. And this can be kind of helpful. So these are actual radius values of the atoms in group 1A, hydrogen, lithium, sodium, potassium. And those numbers there are in picometers. A picometer is 10 to the minus 12 meters, so pretty small. But what I want you to see here is that all those atoms are getting bigger as you go down. So as you go down the periodic table, from hydrogen to lithium, lithium to sodium, the atoms do get bigger. So you have more protons, more electrons running around, pretty crazy. So atoms get bigger as you go down the periodic table. They generally get bigger as you go left across the periodic table as well. The atoms on the right kind of tend to get shielded a little bit, and the atoms on the left don't. So this is an example of chlorine through sodium, and you can see that pretty much the atoms are getting bigger as you go left. So someone asks you a question, i.e. your instructor, which atom is bigger, sodium or magnesium? You would say sodium, because sodium is more left on the periodic table than magnesium is. And if I asked you which atom was bigger, rubidium Rb or sodium Na, you would say rubidium Rb, because that's more down on the periodic table. And if you know that, that's pretty awesome. That's all we need to worry about. This picture shows a lot of atoms from the periodic table, and I just want to highlight how this is not perfect. Now, earlier we said that sizes get bigger as you go left and down, and there are definitely some examples where the atoms are not getting bigger. So antimony is not bigger than tellurium, all right? Even though antimony is more left, it is smaller, all right? And that's just something to think about. On the other hand, arsenic there is bigger than germanium. So germanium is more left, but arsenic is bigger. So again, these rules are a little bit cheesy. However, if you're in the hallway and you don't have access to Google and stuff, and someone from Chem 104 or whatever asks you, which atom is bigger, Dr. Russell, rubidium or strontium? Well, now you know my secret. More often than not, left is bigger as you go on left on the periodic table. So rubidium bigger than strontium. And the same thing for down. So barium would be bigger than strontium, stuff like that. But again, it's not perfect. This is a question you might see. It says, which of these has the largest atomic radius, the largest size? And again, you want the atom which is most left and down on the periodic table. So if you have a periodic table next to you, definitely the one that's most left and down is sodium. Sodium is most left and down on the periodic table. Carbon is be most up and to the right. You'd go left to boron. You'd go down a little bit and left to aluminum. I guess just left to aluminum. And then sodium is the most left and down of all. So that would be how these work. Again, they're not perfect, but it works more often than it doesn't, and that's why it's worth talking about. Now, when it comes to ions, we have to distinguish here between cations, positive ions, and anions, negative ions. So if lithium goes to lithium plus, it loses an electron. And lithium plus has 2 electrons and 3 protons. So the protons are able to hold on to those 2 electrons a lot better than if you have 3 protons and 3 electrons. So notice that 152 picometers for neutral lithium goes to 60 picometers for lithium plus 1. Cations are always smaller than the atoms from which they came from. You have more protons able to hold on to those electrons. Those electrons kind of shrink in a little bit. So cations are always smaller than the neutral atoms they come from. However, if you're making an anion, so for example, we're going to talk about fluorine here going to F-1 fluoride, then we're going to see that those generally are bigger than the atoms they came from. So anions are bigger than the atoms they came from, while cations are smaller than the atoms they came from. And that'll be important here for a little bit. However, if you look at all the sizes of the ions on the periodic table, and if you're able to understand that anions, which are kind of to the right of my line, versus cations on the left, then generally you can see that generally atoms get bigger, ions get bigger, left and down. But you should really only compare one to the other. You shouldn't compare like cations and anions together. All right? So the anions are the black ones on the right-hand side, and the cations are the black ones on the left-hand side. So let's focus just on the cations. Beryllium is smaller than lithium, so that means lithium is bigger. Going left makes it bigger. And also, if you go down, you can see that sodium is bigger than lithium, rubidium is bigger than potassium, etc., etc. So in terms of just cations, left and down works really well. Now on the right-hand side, we need to look at the black lines as well. And generally speaking, left and down works well. But you can only compare anions to anions and cations to cations. You can't compare anions and cations together or stuff like that. Now, like before, there are exceptions. So telluride, T2-, is smaller than iodide, which is 220 picometers. So again, they're not perfect, but overall, it's a fairly good thing. Although now that I say that, I just realized selenium is smaller than bromide. Well, anyway, ultimate answer. If you can look these things up in Google, something like that, of course it's better. All right, because then you have the actual numbers to look at. But again, someone from Chem 104 talks to you outside the bathroom or something and says, which one's bigger? Even you now can say, well, left and down works pretty well, but only compare cations to cations and anions to anions. So here's an example of a problem you might see. It says, which of the following should have the largest radius? These are all anions with a neutral atom. But what's important here is they're all on the same level of the periodic table. So left and down is what you generally want to follow. So argon would be most on the right, chloride would be next, sulfide would be next, and phosphide, P-3, is most left and down. So for all of those, we would say for that reason alone that phosphide is the biggest. Now, you can also think about it in terms of protons and electrons, and you can see here how phosphide has fewer protons. They all have the same number of electrons. So the more electrons there are per proton, the bigger the atom's going to get for that reason too. So phosphide will certainly be the biggest of all of those ions. Ionization energy is the energy required to move an electron from an atom. And there's different types of ionization energy. So the first ionization energy would be the energy required to remove a single electron. A second ionization energy is possible, though, too, because you can take that now singly ionized atom and remove a second electron from it. So the first ionization energy is the energy required one electron, and the second ionization energy would be the energy required to remove the second electron. Now, metals lose electrons a lot more easily than the nonmetals. So generally speaking, ionization energy is the opposite of our sizes. Ionization energy generally increases up and to the right on the periodic table, so the opposite of the sizes. Now, like everything, ionization trends are just kind of a trend, and they're not perfect. But you can see there helium versus hydrogen. Helium is more up and to the right, so it definitely has a higher ionization energy. And when you look at lithium through neon, generally it goes up and to the right, the energies increase. But look, nitrogen is higher than oxygen, and beryllium is higher than boron. So there are some deviations amongst this. It's not totally perfect. But again, someone accosts you in the middle of the hallway and you don't have access to Google or don't want to look it up, whatever, generally speaking, up and to the right works better. So you can see here, helium is most up and to the right. It's higher than neon, which is the top of the next one, which is higher than argon, etc., etc. Electron affinity is the energy change that happens when an atom accepts an electron. And there's lots of differences here. Electron affinity, in my opinion, is the weakest of these trends. But for some elements, energy is actually released, like you get energy out. It's exothermic. Other ones, it's positive. It can be all over the place. Electron affinity is not always as helpful as ionization energy and the sizes are they, but it's a cool thing to think about as well. Some elements require energy to have the electron added in. Some of them have energy given out. It just kind of depends on the different element you're looking at. But again, more or less up and to the right is the way to think about this. But again, it's not perfect. Now, up and to the right is by far the cheesiest. So first of all, helium doesn't want to add any electrons, so it doesn't count in this game. And generally speaking, though, it's up and to the right. But one thing that's always perplexed me is why, if you look here in the upper right hand corner, why in the world chloride is higher than fluorine? Like, why making chloride you get more energy out, negative, than if you made fluoride? So it's kind of, I hate to say cheesy, but electron affinity is less helpful, shall we say, than others. But if you're asked a question, up and to the right is the name of the game. This last section we need to talk about now is how to make some compounds, and this will be an ongoing discussion, but nomenclature is the ability to name compounds, and this is so important because if you don't know what chemicals you're working on, it can be really tough to deal with. Now, nomenclature in this textbook is split into Chapter 3 and Chapter 4, so we'll kind of do some of it here. We'll keep talking about it as we go through. But anyway, in ordinary chemical reactions, it's usually not the nucleus of the atom that changes, but it's the electrons around it. And there's two types of bonds that can be made. And you can think of these bonds as being the glue that holds electrons together. You can make ions, which is when an electron is actually transferred from one atom to the other. So an ionic bond is usually between a metal, which gives up an electron or electrons, and usually the thing that's accepting the electron or the electrons is going to be the nonmetal. So sodium chloride would be a good example of that. Sodium loses an electron and chlorine gains an electron to make an ionic compound. But on the other hand, there are lots of examples of where molecules share electrons, and those are called molecular or covalent compounds. And they're both really important. Covalent compounds are not as strong generally as ionic bonds, but they can be really useful because life needs a lot of bonds that are acting really fast. Covalent bonds are much more flexible, and so being flexible gives covalent bonds the kick up on life. So most of the things we deal with in life use covalent bonds, but ionic bonds certainly have their use too, and we'll see this as we go through the class. But if you have to make an overall thing, usually ionic means metal plus nonmetal, and usually covalent means nonmetal plus nonmetal, but we'll see exceptions both directions as we go through the class. All of the metals And all of the nonmetals can fall into basically two important categories for us right now. First, we're going to talk about fixed ionic charges. Fixed ionic charge means that the atom always has the same charge, so they're predictable. And there are both nonmetals that are fixed charge and there are metals that are fixed charge. Nonmetals are the easiest because most of them, to figure out their charge, you take the group number and subtract 8 to figure out their ending. And as I've kind of mentioned before, but I'll say formally here, you want to name that anion, that negative ion, with an IDE ending. The metals, on the other hand, there's only a couple types of metals that have fixed charges. And the fixed charge metals fall into group 1A, they fall into group 2A, and they have the stairs. So group 1A would be sodium, potassium, lithium. Those group 1A metals are always going to be +1. Group 2A metals would be calcium, magnesium, strontium, barium. They're always going to be +2. And then the stairs is this funny group on the periodic table. It starts with aluminum, number 13, and goes down to indium, number 49. And you can see it goes left to silver. So it's like you have a single step, 2 steps, and 3 steps. So what this means, the step number represents the charge. So silver is always +1, cadmium and zinc always +2, and indium, gallium, and aluminum always +3. So that's why they're the stairs. +1 in the first step, +2 in the second step, +3 on the third step. Now, the reason why these nonmetals and these metals are important is because they're always going to have the same charge, at least for us in the Chem 200 series. So zinc will always be +2. Sodium in group 1A, always +1. And for example, chlorine in group 7 on the periodic table will be 7 - 8. Chloride, always -1. So the predictability makes this very attractive. So chlorine in group 7A becomes 7 - 8 -1, and it becomes chloride. Oxygen in group 6A becomes oxide, O2-. Phosphorus becomes P-3 phosphide, etc., etc. The main group metals, +1, sodium, +1. Magnesium becomes magnesium, +2. And again, the hip chemist will always know that magnesium is +2 and phosphide is -3 when they're coming together to make bonds. These are the fixed ionic charge metals and nonmetals. What is the probable charge on a barium ion? All right. So what we would do to figure this out, we would see where barium is on the periodic table. Its atomic number, Z, is 56, so that means 56 protons. But important here, barium 56 is in group 2A. It's an alkaline earth metal, and all the alkaline earth metals in group 2A are going to be +2. So we would predict barium to have a +2 charge, and 99.9% of the time it is +2, just like strontium above it, just like radium below it, stuff like that. They're all +2 in that group. All of the other metals, though, on the periodic table, and there's a lot of them, so group all the transition metals except for the stairs, the lanthanides and the actinides, there's some metals under the nonmetals, all of those are variable charge metals. And what that means is that even I, with my PhD, I would not know what the charge is. So we need a way to talk to each other about what the charge is going to be. And chemists use a Roman number to talk about it. So Roman numbers are used with all the lanthanides and actinides, all the non-stairs transition metals, a couple metals under the non-metals, a lot of them. Now, the Roman numerals are on the right there. So Roman numeral 1 is just the I. Roman numeral 2 is like II. 4 and 6 are what people mix up. 4 is IV, and 6 is VI. So just kind of FYI about that, we'll need to use those. So iron +2 would be iron Roman numeral 2 like that. That's how you'd write it. Now, you don't write the Roman numerals in formulas, but you would when you're talking about the names, and we'll talk about that. Iron +3 would be iron Roman numeral 3, III. Do not use ferrous or ferric nomenclature if you know what that is. If you don't, just ignore what I'm going to say here. Ferrous and ferric is old school and not used as much. Use the Roman numerals. Don't use ferrous and ferric. Likewise, uranium plus 4 would be uranium IV to say it's a 4. Lead 2 plus would be lead 2 II. Lead 4 plus would be IV, etc., etc. So notice if you just said iron, I wouldn't know if it was iron plus 2 or iron plus 3. Or if you said just lead, I wouldn't know if it was lead 2 or lead 4. So the Roman numeral helps us to talk to each other about what the charges are going to be on these things. In addition, there are some combinations of atoms that come together. They're very stable and they have a charge. And these crazy things are called polyatomic ions. Poly means many, many atomed ions. And they're very common. They're more common than some of the other ions we've talked about. So a real common example of this is nitrate. Nitrate has 1 nitrogen, 3 oxygens, and a -1 charge. So nitrate NO3 minus 1, and sulfate SO4 minus 2, and hydroxide, another common one, OH minus 1. You kind of need to sit down and memorize these things. And I hate using the memorize word. I really do dislike using it. But that's kind of what you have to do to knock these out. So on the right-hand side here, I have a list from the Nomenclature Lab, which is the complete list of ions that I kind of want you to think about. And if you can go through and figure these out, you're good to go. Now, there are some patterns. So for example, you can see right in the upper left-hand side, there's a nitrate and a nitrite. And nitrites generally have less oxygen than nitrates. So here's phosphate, PO4 minus 3. Phosphite has 1 less oxygen, PO3 minus 3. So there are some kind of patterns like that. But try to go through and figure these out, memorize them. You can make flashcards. I have cheesy flashcard things on the website and the companion you can use. You can use Quizlet if you want to go through that and memorize them. But when you hear nitrate, you need to think NO3 minus 1. And if you see NO3 minus 1, you have to think nitrate. So start memorizing those. They will be very helpful to you. So which of these polyatomic ions probably does not contain oxygen? Here's another kind of hint that I can give you. When it comes to those polyatomic names, a lot of them have ATE and ITE endings. And anytime you see ATE or ITE, ATE, those almost always mean oxygen. So the only one here which doesn't have ATE and ITE would be cyanide. So we would guess, and guess correctly, that cyanide does not contain oxygen. It doesn't have an ATE or an ITE suffix. So that's one other hint that I can tell you to kind of figure these out. But again, just kind of start going through them, figure out how this works and stuff, and you'll be good to go. You can also learn about my friend Nick the Camel. Nick the Camel Brat ate icky clam for supper in Phoenix. And you're like, what the heck is this all about? Believe it or not, this is a way to help you learn not only the polyatomics, but it can actually help with the acids too. So Nick the Camel Brat ate icky clam supper in Phoenix. Nick has nitrogen, so that's the first letter of the polyatomic ion, and everything else is going to be oxygen. Now notice in Nick you have 3 consonants. Vowels are A, E, I, O, U, sometimes Y. Consonants are everything else. So N, C, and K are consonants. That means that there's going to be 3 oxygens. So 3 consonants means 3 oxygens. And there's 1 vowel. That means the charge is going to be -1. So nitrate, NO3 minus 1, has 3 consonants, 3 oxygens, 1 vowel, -1, and it begins with N. And this is what sometimes people will use to figure these things out. So you can keep going. Down next, kind of close to the bottom, supper begins with S, so that's a sulfur. Has 4 consonants, 4 oxygens, 2 vowels, U and E, -2. Anyway, some people dig this. You don't have to use it, but it is something that's available. Chromate is another one we throw in sometimes, so that's also a possibility. Anyway, if you dig Nick the Camel, cool. If you don't, it's no problem. It's just an option for you to learn. So when you have an ionic compound, you have metals that have lost electrons and nonmetals that have gained electrons. And to make an ionic compound, you have to have equal positive and negative ions. And when you're naming the ionic compounds, it's metal first, followed by the nonmetal IDE ending second. And these aren't usually too bad as long as you know what the respective ions are. So let's say you wanted to add chloride and sodium. Well, chlorine in group 7A gains 1 electron, 7 minus 8 is 1, becomes -1 chloride. And sodium in group 1A likes to lose 1 electron to become sodium plus. So sodium plus Cl minus, +1, -1, charges cancel, NaCl is the formula. Sodium chloride would be the name of that compound. Let's say you wanted to combine calcium and bromine. Well, bromine, like chlorine, is in group 7A, so it's going to be -1 bromide. Calcium, though, is in group 2A. It's a +2 because it's in group 2A. So when you make a neutral compound, 2 and 1, you're going to need 2 minus 1 bromides to cancel the +2 calcium. So calcium bromide CaBr2. You can see how there's no net charges at the end. You could turn the calcium bromide name back into a formula by knowing that calcium's +2, bromide's -1, and you need 2 of them to make a neutral compound. You can do the same thing with polyatomic ions. Nitrate is -1, magnesium's +2. So when you make a neutral compound there, you make MgNO3 magnesium nitrate. Now notice the use of parentheses. If there's more than one polyatomic ion, you use parentheses. Otherwise, you never use polyatomic ion, otherwise you never use parentheses. Only if there's more than one polyatomic ion. Here's an example of that. Potassium and nitrate would be a +1, -1. That would be written KNO3, potassium nitrate, no parentheses. Only use parentheses if there's more than one polyatomic ion. That's really important in chemistry. Here's some more examples. You can have fluoride, which is F-1. You can also, though, use variable charge metals. So here's an example of an iron +3. So you'd write that as iron Roman numeral 3. Now, because iron is +3 and fluoride's -1, you're going to need 3 minus 1s to cancel that +3. So FeF3 would give you neutral compound, +3, and 3 minus 1 minus 3 from the fluorides. You'd call that iron Roman numeral 3 fluoride. You don't put the Roman numeral in the formula. It's only used in the name, just so you know that. Oxygen and aluminum. Aluminum is fixed charge, +3. Oxygen's -2 because it's group 6, 6 minus 8 minus 2. If you combine those two together, 3 times 2 have a common denominator of 6. So if you want to figure out how many oxygens, common denominator 6 divided by the charge 2, you're going to need 3 oxygens. And 6 divided by charge on aluminum 3 gives you 2 aluminums. So Al2O3, aluminum oxide. Manganese, Roman numeral 4, would be Mn +4, and sulfate, SO4 -2. You're going to need 2 sulfates to bond with the manganese, so you'd write that Mn parentheses SO4 parentheses 2. That would be manganese 4 sulfate. And again, you need the Roman numeral because manganese is not group 1A, group 2A, or the stairs. All the other metals, you need to use Roman numerals on them. You can also use the polyatomic ion ammonium, which is positive, to react with things. Ammonium chloride would be NH4Cl. Again, no parentheses because we're only using one polyatomic ion. Chemistry. A covalent bond is usually between a nonmetal and a nonmetal, and electrons are shared, so you don't have positives and negatives. And to designate this difference, because the bonding is quite different, it's not as strong, but it's more flexible, chemists use Greek prefixes to talk about how many atoms there are. The second atom always gets an IDE ending, but you want to use Greek prefixes. Now, Greek prefixes are mono, di, tri, tetra, penta, hexa, etc., like that. that and stuff. Tetra is 4, not quattro. I see that sometimes. 2 is di, not bi, which I see sometimes. So the Greek prefixes are used. So NO would be nitrogen monoxide, or monooxide is okay. Usually the double vowels are omitted, so it's just monoxide, but either way is fine. Nitrogen, one nitrogen. Mono means one oxide. You always use a Greek prefix on the second atom, but the first one, you only use it if there's more than one. So as an example of that, N2O. N2O would be dinitrogen monoxide. So here we have more than one nitrogen. We're going to need to use a Greek prefix on the first one too. But the second one always gets a Greek prefix, and the second one always is IDE. So SF6 would be sulfur hexafluoride, S2Cl2, more than one on the first one, disulfur dichloride, P2O5, diphosphorus pentaoxide. You get how this works out. So N2O4, if you want to have a name for it, there's more than one of the first one, so we need to use a Greek prefix. That would be di. There's 4 of the second one. 4 is tetra, and you want to give that last one an IDE ending. So N2O4 is dinitrogen tetraoxide. Briefly, acids are really important to chemistry because they have a lot of energy associated with them. And acids are so important that usually the H is listed first. So this is an example of hydrochloric acid, HCl. The H is listed first. Most compounds, H's aren't listed first because they're not that exciting. But with acids, oh yeah, they're exciting. Now, technically, an acid is only an acid if it's dissolved in water. And dissolved in water, you get the symbol AQ, which stands for aqueous. So notice down here, hydrochloric acid in water is HCl AQ. It's in water. Hydrogen chloride, or sometimes hydrogen monochloride, it'd be just gas. There's no water. You really need the water to make an acid an acid. We're not going to make a big deal of it yet, but this will be important to us later on. So hydroiodic acid is HI. Hydrogen iodide would be the gas version, etc., etc. Nitric acid is HNO3. That would be HNO3 in water. We'll talk more about acids in the nomenclature lab. So acids are important, but bases are too. And so bases are metal hydroxides. And if acids are yin, then bases are yang. They're kind of the opposite of each other, and they're both really important. So bases are metal hydroxides. Sodium hydroxide is the most common base, probably. Sodium is a metal. Hydroxide is a polyatomic ion. And so in water, it breaks up into Na plus and OH minus ions. This is what Drano is all about. If you ever use Drano on a hose and a sink in your house, you're using sodium hydroxide. NaOH, KOH, LiOH. Notice the thing of OH, and again, metals lead the compound there. So sodium hydroxide, potassium hydroxide, lithium hydroxide. There are some nonmetals with hydroxide. So, for example, C2H5OH is ethanol, and that is not a base because C2H5 is not a metal. You have to have a metal there. Again, we'll talk more about this in the nomenclature lab, but I just wanted to throw it in here.
When the hydrated compound, copper sulfate pentahydrate, is heated, the water molecules associated with the ionic solid are driven off, leaving copper sulfate with no associated waters. This compound is called anhydrous copper sulfate.
Some ionic compounds have waters associated with them. So if you look down there at the bottom, this CuSO4.5H2O, that has 5 waters connected to the copper 2 sulfate. So this is called a hydrated compound. And hydrated compounds usually have a really nice color. And when you take the water off by heating it, they lose their color and they become anhydrous. So if you see one of these, you just use the regular name plus Greek prefix hydrate. So as an example, this CuSO4.5H2O, you would call it copper 2 sulfate. Copper is a transition metal, so it needs a Roman numeral for the Roman numeral 2. Sulfate is always -2, copper 2 sulfate. But because it has 5 waters, you'd call it copper 2 sulfate pentahydrate. The next one would be magnesium sulfate with 7 waters. That's the Greek prefix hepta. So magnesium sulfate heptahydrate. And you could have anhydrous copper 2 sulfate, which would be copper 2 sulfate without the waters, nickel 2 chloride hexahydrate, etc., etc. So not too difficult, but if you see one of them now, you'll know what to do. So why is nomenclature important? Arguably, it's the most important of all, because adding or subtracting a single atom can make a huge difference in what's happening. So this is a really old poem. Auntie Jane fed baby Nell what she thought was calomel. What the baby really ate was corrosive sublimate. Not much difference, I confess, just 1 chlorine more and 1 baby less. What the heck, Russell? Well, here's the joke about this. Not really a joke. I say, hey, shut up, kid. No, I'm just joking. Calomel is mercury with 1 chlorine, HgCl. And HgCl apparently uses for dysentery. It's used to make medical reasons. So this would be a good version of mercury with chlorine. But if you add 1 extra chlorine, mercury with 2 chlorines, mercury 2 chloride, it becomes a poison. This is bad news and stuff. So you don't want to give the poor little baby the corrosive sublimate. That would be a death sentence. Calomel, though, can actually have good uses for things. So just 1 extra atom can make a huge difference in the reactivity. This is one of my favorite jokes, quote unquote. This is 2 chemists in a bar. First chemist goes, I'd like to have some H2O. And the second chemist goes, yeah, that sounds pretty good. I'll have some H2O too. So the bartender hands them both something that looks just like water. The first chemist drinks it down, no problem. Second chemist drinks it and dies. And the first chemist goes, idiot. Well, here's why. H2O2, 1 extra oxygen atom, is hydrogen peroxide. And you don't want to be drinking hydrogen peroxide. That stuff is nasty. On the other hand, H2O, everybody needs it every day. So the nomenclature, super important. So wow, this nomenclature stuff, pretty important. Spend some time kind of figuring it out. We can talk to each other about the right chemicals to use and avoid the chemicals which aren't right to use. You'll be good to go. Okay, so that's the end of this chapter. Thank you for hanging out with me and all this. If you have any questions, of course, let me know. This was an important chapter, but it's all stuff you can do. And again, lots of things are here. You can talk to the Avid LSC Center above the MHCC library. mhcc.edu/LSC is their website. And of course, I'm always here to help too. All right, have a great day. Thanks for being here.